Problem number 46 of section 1.6.1 asks us to explain why the function f of x equals ax to the fourth plus bx cubed plus cx squared plus d can only have at most two inflection points. Now recall that an inflection point is a point where the concavity changes. And where the concavity changes, you have to look at the points where the second derivative is equal to 0 and then see, does it change when you go from one side of the inflection point? Does the sign of the second derivative change when you go from one side of the inflection point to the other? And of course, you always also have to check points where the concavity might change at where the second derivative is not defined. So we'll start out by computing the second derivative of f. So the first derivative will be 4a x cubed plus 3b x squared plus 2cx, and the derivative of a constant term is just 0. Now the second derivative will be 3 times 4, 12, ax, and I'll bring down the power, so we have squared, plus 6bx plus 2c. Now, the second derivative is defined everywhere. This is just a quadratic. Now we need to check what are the points where this is equal to 0. How many points can this have, or how many possible values of x are there? Well, we know from algebra that a polynomial of degree n can have at most n roots. Well, here we have a quadratic, or a polynomial of degree 2, so it can have at most 2 roots. In other words, at most 2 inflection points. Now this polynomial, or this quadratic, will have 2 roots, but they may or may not be distinct. If they are not distinct, then all that means is there's only one inflection point. But this thing is guaranteed to have at least 2 roots and at most 2 inflection points.